Hello everyone, my name is Julian Morgano, and today I'm going to discuss a bit about light blackbody emitters and emission line spectra. The three main objectives in this experiment involve using atomic emission spectroscopy to analyze the experimental data. The experiment will be sectioned into three components, such as the speed of light, blackbody emitters, and emission line spectra. In terms of the bigger picture and purpose, measuring the speed of light can help with understanding the relationship between distance, time, and the movement of light, especially with celestial objects and the transmitted light through telecommunications. The speed of light is also useful for pinpointing light interactions and, in turn, how this affects the emitted light. Blackbody emission spectra allows people to estimate the emitted thermal radiation of stars and other celestial objects. Using the important laws and/or equations provided from Planck and Wayne for blackbody irradiation are essential for understanding wavelength and energy emission in our universe. It's important to identify blackbody emitters and differentiate them using Planck's best fit approximation. For the emission line spectra, we can forge distinctions between element isotopes. The unique spectral lines emitted when atoms undergo electronic transitions indicate that atomic energy levels are indeed quantized, supporting quantum theory. By comparing experimental and theoretical values between hydrogen and deuterium, this can help validate quantum mechanical models on different atoms. My main two hypotheses highlight blackbody radiation and the emission line spectra for hydrogen and deuterium. I predicted that the minimum peak wavelength of the blackbody emitter would gradually decrease to short wavelengths when the temperature increases due to the amount of photon energy between electronic transitions. My second prediction underlined how hydrogen would shift to lower wave numbers due to a lower reduced mass in the same electronic transition as deuterium. Here are some important fundamental equations. The first equation relates the speed of light constant c to the change in time delta t, as well as the double length due to the full round trip taken between the detectors and the mirror. The second equation, Wayne's displacement law, consists of the maximum peak wavelength multiplied by temperature T released from the black body emitter. This equals the Wayne constant value B in units of nanometers times Kelvin. The next equation is Planck's law for blackbody radiation, which measures the relative intensity of light emission. The Rydberg formula consists of the wavelength, principal quantum numbers n of the electronic transition, and the Rydberg constant. Bohr then corrected the Rydberg formula to account for the reduced mass mu, the electric charge E, the permittivity constant epsilon. Equation 6 represents the energy of the emitted photon. The Rydberg mass equation 7 consists of all masses for deuterium and hydrogen. Now we move on to the experimental setup for determining the speed of light. On the right-hand side of the screen, in Figure 1, you could see various optical equipment that were able to manipulate the trajectory of the low-powered red laser beam. All optical pieces were placed on a platform and can be easily moved around into other positions. In Figure 1, equipment A is the low-powered laser source that projects an outgoing pulse of light, whereas equipment B represents a beam splitter that divides the incoming incident light into two different directions. One pulse of light enters detector C, located at the top section of the image. Meanwhile, the other portion of the light pulse reflects off of the mirror shown on the left-hand side of the screen. The experiment actually utilized a small mounted mirror to redirect the light. The mirror was adjusted accordingly in order to reflect the outgoing light back in the opposite direction. To help locate the beam, a piece of white poster board was placed in front of the mirror to confirm the intended trajectory. The return light pulse then passes through lens D to help create a focused image of the returning light reaching the detector E. Now for the speed of light results, there's a lot of deviation between the actual speed of light and then the calculated values in Table 1. The speed of light values start to increase rapidly at measurement 3. Accidentally misinterpreting the measuring distance most likely skewed the results. In Figure 2, the oscilloscope recorded two light pulses. One is the outgoing pulse that passes through the beam splitter. The other portion of the light pulse reaches the detector. and the other reflects off the mirror. The reflected light pulse corresponds to the returning light. Since it reaches the second detector after doing a full wraparound, the time difference for the first measurement is actually 90 nanoseconds. The oscilloscope reading indicates how long the laser took to reach the mirror, then come back to the second detector. Now, for the black body emitter setup, there's various light bulbs plugged into a single power strip. This experiment only used 4 light bulbs used for comparison: an LED bulb, a compact fluorescent bulb, a halogen bulb, and an incandescent bulb. In figure 3, there is a blue fiber optic cable positioned closely to each light bulb along the power strip, which transfers the emitted light to the spectrometer, depicted in figure 4. Each bulb emits a different distribution of frequencies, wavelengths, and energies based on the type of emission mechanism the light source uses to produce light, as well as the kind of material within the bulb. This distribution can then be used to determine the temperature measured in units Kelvin. For the blackbody emitters results, we see different measurements recorded from the spectrometer represented by the colored wavelength spectra curves. Planck's approximation is the white curve just above the colored curve. What you'll notice about the 11-watt LED bulb and 23-watt compact fluorescent bulb is that the Planck's approximation doesn't support these light sources compared to the halogen bulb and the incandescent bulb, depicted on the right side of the screen in figures 6 and 7. This is because the 11-watt LED bulb and the 23-watt fluorescent bulb contain sharp, narrower peak wavelengths. Blackbody emitters produce continuous spectra, similar to a bell-shaped curve, because the emission process isn't restricted to the discrete energy levels, and the continuous energy exchange between the emitted light and materials via the light bulb filaments results in a smoother distribution of energies. The fluorescent bulb showcases a discontinuous spectra due to the excitation of gas atoms. The sun accurately reflects Planck's best fit approximation curve, since it is due to the high gravitational pressure on its hydrogen and helium gas composition. You can see that the sun ground level Planck's best fit approximation looks a bit off compared to the outer atmosphere due to the larger distance. The fiber optic cable was positioned near the window to try and get the spectrometer to record the spectra for the sunlight. According to the data provided in Table 2, the LEDs and fluorescent bulbs do not contain necessary filaments required to radiate heat when the electric current passes through them. LEDs use semiconductor materials to produce light, whereas the fluorescent bulb relies on the gas discharge to emit light. Halogen and incandescent bulbs are typically hotter because they have a thin filament material that can produce thermal radiation. These bulbs are not perfect black bodies due to the Planck approximation, but they do share a similar spectra to the sun. Applying the Planck's law or Wien's displacement law to the LEDs and fluorescent bulbs to determine their temperature can give inconsistent results and won't accurately reflect their true temperature. On the other hand, the sun's outer atmosphere turned out to be the hottest and followed Planck's best fit approximation, because as the temperature increases, the peak wavelengths approach shorter wavelengths. This concept of light emission also relates to the line spectra of hydrogen and deuterium isotopes that will be mentioned here shortly. For this part of the experiment, a hydrogen and deuterium discharge lamp was properly aligned next to a monochromator approximately 60 meters away. A biconvex lens was placed in the center, and this created a focused image of the discharge lamps so that the light can enter the monochromator entrance slits. The lens and slits alter the incoming light, allowing the monochromator to detect and disperse the light into separate wavelengths. Overall, the monochromator helps reveal the discrete energy levels in hydrogen and deuterium, with narrower maximum peak wavelengths deviating from the continuous spectra seen with blackbody emitters. Now, according to the emission line spectra results, here we have 2 monochromator signal scans for both hydrogen and deuterium, both of them which have singlet and doublet peaks, and there are actually 6 doublet peaks shown. The hidden one is around 3,850 angstroms. The slightly shorter spectral line wavelength doublet peak represents deuterium due to a larger reduced mass, whereas hydrogen appears at slightly longer wavelengths. Each doublet peak is the same transition, where both hydrogen and deuterium isotopes follow the Balmer series for electronic energy transitions. Only transitions between quantum numbers n equal to 9 to n equal to 2 levels were part of the Balmer series, because these lie in the range of visible light spectra. Higher energy levels and quantum numbers have faint and thin spectra due to the limit of a low wavelength of 364.6 nanometers. Now we move on to the emission line spectra results, where tables 3 and 4 both provide hydrogen and deuterium maximum doublet peak wavelength values. These values correspond to the electronic transitions according to the Balmer series. This accounts for only the visible light spectra. The experimental speed of light value was used to determine the experimental energies for the electronic transitions between the ground and excited states. These energies were high because the calculated speed of light turned out to be exceedingly high as well. The quantum number n equal to 9 to 2 electronic transitions were computed for both hydrogen and deuterium below each table. Additionally, moving further away from the atomic nucleus means that the energy levels decrease, so it takes less energy to transition from the higher energy levels at quantum numbers 8 to 9 compared to the lower energy levels from 4 to 5. Based on the inverse wavelength versus the quantum number squared according to the Rydberg formula, you'll notice a linear trend used to determine the experimental values for the Rydberg constant. The Rydberg constant was found directly from the slope values given in the slope-intercept equations in figures 15 and 16. The Rydberg constants did differ slightly between hydrogen and deuterium, meaning that the monochromator measurements accurately support the difference in values between isotopes. Also, the decreasing relationship between the inverse quantum numbers and wavelengths further complement the linear slopes. Here, the theoretical and experimental Rydberg constants were compared, and these gave a relatively low percent difference, meaning that the experimental wavelengths obtained from the monochromator appear to be mostly accurate, with a minor discrepancy likely caused from the high speed of light value. The experimental mass of deuterium had a much lower value in comparison to the theoretical mass because the Rydberg constants were smaller. The ionization for deuterium will be larger than hydrogen since the atomic nucleus strengthens the electrostatic attraction between the electrons in the nucleus. In conclusion, my hypotheses were proven correct. For the first prediction, the maximum peak wavelength will approach shorter wavelengths as the temperature increases. This was proven by applying Wayne's displacement law on light bulbs in the sun. This results in a higher energy required for light emission. For the second prediction, since the wave number is inversely proportional to the wavelength, increasing the wavelength would lower the wave number values slightly because hydrogen and deuterium isotopes slightly differ based on the reduced mass.